Now, today we're going to look at a very big item and a very interesting item, to be honest, in the new course part of the networks and graphs called scheduling. And scheduling is where you're planning an event in which there are many activities, something like a wedding or building a new school. And one event can't happen until another event is done. So in other words, you can't have the plastering the walls until the walls are built. Now you could have simpler things like making a bed or something like that. Not making the bed, building a bed, which might have 7 or 8 activities. Now, in this one here isn't an actual one. It's just a schematic schedule. And what I just want to show is, what does this mean? Well, obviously, the activities are the arcs. 0, 1, 2, 3, and 4 are called events, but they're not events. They're simply the turnaround when one activity is over and another one may begin. It's when the gaffer hollers, "Okay, let's start B now." That's the event. They're called events, but they're not really events, if you ask my opinion. So you can see here that B can only take place when A is completed. A doesn't depend on anybody, so we put a little blank for that. You will notice that B cannot happen until A is completed, so we put that down when activity B depends on A. C, let's have a look at C. C doesn't depend on any other activity before it. What about D? Well, D will not be able to be done until both B and C are completed. So it depends on both B and C. E depends on D. F also depends on both B and C being completed. And finally, G depends on both E and F being completed. And that is called our precedence table. And that's part of the art. Now, if we go on and do things the other way, it's a lot more complicated and it can go wrong. That's the interesting part. You will often find that your first attempt, it has to be abandoned. So here's the precedence table for making a cup of coffee. You have to put the real ground coffee in the cafetiere, get milk from the fridge, fill the kettle, boil the kettle. Well, obviously you can't boil the kettle until you fill the kettle, and so on. So we have a precedence table. So what will the chart, what will the activity chart look like? Now, you can start with this thing called an event 0 or 1. Usually we start at 0 or 1. It doesn't matter which you want to call it. But A and B and C don't depend on anything, so they will emerge from there. So there goes A, B, and C. Now, after that, D is the next one, and it depends on C. So I should put the arrows there. We'll call this 1, 2, and 3. D depends on C. We'll call that 4 there. And B depends on E. Sorry, E depends on B. I forgot to put that, it was D. Now, F depends on both A and D. Uh-oh. So A and D have to converge so that F will emanate from them. So that's not what I'm going to do. I'm going to do something like this. Put C up here and have A and D then converging. So my first attempt was a failure, and here goes my second attempt. I'm going to put B up at the top as I planned there. That's B. I'm going to put A underneath that. And then I'm going to put C on its own down here. The numbers don't matter. Now, B goes on to E, and A leads on, and C leads on to D, yes. Okay, well, I put them upside down, but it doesn't matter. There's D. We have to get A and D converging. So I'm going to bring this here to there. That's A converging here and A and D converging so that F can emerge from there. So that's our new plan. And B then goes on to give us E. That's 4. And what happens next? E and F have to converge. So really, I want this F to go up there. Since I have made such since I have got so many things wrong, this is my third attempt. And in the book, I go through these 3 attempts one by one, just to show that it is quite a normal thing to make more than one attempt. So A goes on here to 2, and C and D converge on 2. And E emerges there. And now things are perfect because we have B, sorry, that's F, and E, and A. And now we have E and F converging here, and G depends on them. And finally, H depends simply on G. And there is the correct table, the correct flowchart for the dependency or precedence table above. It took us 3 attempts, but we got there. Quite a normal thing to happen. Now, there's a whole exercise in the book on those. Some of them are real life and some of them are simply schematic. And now we come to the idea of a thing called a dummy activity. What's a dummy activity? Well, when we examine the following very simple chart, the W and X depend on nothing, but Y depends on W being finished, and Z depends on both W and X being finished. Let's try, that's a very simple chart, you think that's going to be easy, but look at the problem it throws up. W and X depend on nothing, so they emerge. Here, just for pig iron, I'm just calling the what we call the source node, the start, 1 instead of 0. 1 or 0 is the usual source node, as I say, wrongly called an event. But there you are. The activities are the arrows. That's the key thing to understand, that the arcs are the activities or represent the activities. Now, Y we know depends on W. But now we want to show that Z depends on both W and X. How could we do this? If we have Z coming out from W, like this diagram up here, 12.63, that does not show that Z also depends on W. Z also depends on W. So that doesn't show it. Then this one, W and X, Y and Z emerging from W and X is not allowed. You're not allowed to have 2 edges, and Also, so you're not allowed to have two edges between two inverted commas events. You're not allowed to have that. Two nodes can't have two events between them. And the other thing is this implies that y depends on both wx, which it doesn't. Y does not depend on both wx. Y depends only on w. So here's how we resolve the problem. We put, I'm going to draw it over here on the left. We put w and x starting off from the source node. We have y coming from w because it depends on w. And to show that z depends on w, we put an arrow here, and now z comes here with the dotted line. This is called a dummy. It's got no name. It doesn't represent an activity. It's got, later on, it'll take no time or cost no money. It simply shows that this dummy event must happen before Z. It simply shows the precedence that Z can happen only when W has happened. It shows that W and this dummy event, which doesn't really have take any time or do anything, it just simply shows that Z also depends on W. And that dummy activity, showing that to get to 3, you have to have W and a dummy event. In other words, you must have W before we have Z emerging. That is shown by that dummy. Now, a dummy is always shown by a dotted line, and we don't necessarily write the word dummy. If it's a dotted line, it is a dummy. It shows precedence, but it has no weight. So now we're going to do a much more complicated precedence table that will involve dummies. And again, I've just got it started here. I'm using the source node 1. It doesn't matter whether you use 1 or 0. 1 is the source node. Q is the first activity, and it's the only activity, as you see, that has nothing depending on it, so out it comes. R and S and T all depend on Q, so they emerge from Q, and then U depends on R. So I've got that so far. Now, in order to satisfy the next step, let's continue on and show that V depends on both S and T. How can you do that? This is how. We can put an activity there, and we'll call that number 7, and that is V. But to show that V also depends on T, I put a dummy activity there, bringing that to 4, so that V can happen only when S and T are both done. So now I've done shown that. Depending on T on its own is W. That's W. And let's go on. W depends on T. X now depends on both R and V. Well, I can have X emerging from V, and I can put in a dummy activity there showing that X depends both on R and V. Very nicely done. Y has to depend on both U and X. So I'm going to do the following. I'm going to do it again, but, well, is that too bad? That's U now extended around here so that I can show that Y depends on U and X. And finally, W and Y have to come together so that Z may emerge therefrom. So let's show that. Let's try and show that That's Z. Let's try and show that in a proper one. I'm going to do another one down below here. 1 goes to, that's Q. That's R. S. T. Now, W is going to go all the way over to here. R. U is going to go all the way over to here. This is V. But there's a dummy from 3 to 7. Nope, that was a mistake. That's a dummy. Sorry. That was a dummy. We're going to Tipp-Ex out here. Good old Tipp-Ex bottle is going to have to come out. This is all very live and real, but this one is X. There's X. It's this one is U. And then we have Y, and then we have Z. I think we have it right now. Yes, that's it. That is it corrected. This is simply a dummy from 3 to 7. U goes from 3 up to what was 8, 9, but there was no 8, so I'm going to call that 8 now. And T leads on to where Y is. That is correct. You can see, for example, that Z depends on W and Y converging. Absolutely perfect now after a bit of messing. There you go. Now, the other way round is much easier. When we have a dependency table, A, B, and C depend on nothing. They come from this source node, which this time is the number 1. D, you can see, depends on A. G depends on C. Now, what about E? It simply depends on D. F depends on B, but it also depends on A. A must happen before F happens, as shown by the dummy. And then H depends on E, F, and G. So the dummy is important. F depends both on A and B, as shown by the dummy. That's a much easier task than doing it the other way around. And now we come to time, but the element of time. The element of time makes this really interesting. When each of the activities is given a specific amount of time, and we want to calculate what will the entire project, what time will the entire project take? Or it might be what, it will be time. We now look at the time taken for the event, and each event is given two boxes. The top one is called the early time, and that is the earliest time by which all preceding events may be finished. And then underneath it, with the late time, it's the latest time by which all preceding events must be completed without delaying the project. So here's a very simple one. And the time of each event, A takes 3 days, B takes 2 days, C takes 4 days, and D takes 4 days. And that's our project. And there's the precedence table done out. You can see B depends on A and D depends on C. That's all. So the source node, let's go. A takes a minimum of 3 days. So when we get to there, the earliest time by which A will be finished is after 3 days. Now, and C takes 4 days, so that will be 4. So when will we reach what's called the sync node, the end of the project? You look at the following. 3 and 2 would be 5. So A followed by B will take a minimum of 5 days. C followed by D is 8. That's greater. I always say early time is the enormousest of the two. The enormousest or biggest of those two is 8. So that means our project will take a minimum of 8 days. And that's because C followed by D will take 8. 3 followed by 2 would be 5. So they could be finished before the end of the project. Now that is what we call our forward pass. It's illegal in rugby, but not in soccer, and it's certainly not illegal when you're calculating the times on these time charts. Now we do a backward pass, legal in rugby and in soccer, except to the goalkeeper. Now let's go. Let's have a look. We're going to do our backward pass. We're going to start here. 8 take away 4 leaves 4. So that means that the late time for finishing C would be 4. Okay, that's the latest time. But going backwards from here, I should say, whatever the sync node is will be the same above and below, and the source node is always 0088. If I go backwards in time, back to, this would be 6. What does that mean? It means that A could finish as late as day 6, because then we will have enough time to get to B to be done and still have the project finishing within the 8 days, which is the limit. So the earliest time by which we can finish A is after 3 days, and the latest time without delaying the project with which we could finish it is 6 days. C must be done by day 4, because if we delay it at all, then we're going to delay the project. So C must be done straight away at the start. Its early time is 4 and its later time is 4. Now, let's do a more complicated one. And just to say again, the sync node will always be 0, 0, and the sync node, the ultimate, will be the total time and the total time. T for total time, it'll be the same. So let's look at these, including we have a dummy here. And the dummy takes no time at all. Well, the source node is A is going to take 6, C is going to take 7, B is going to take 12. Now, this is an interesting one. To get to here, two arrows lead into this. So let's look at which is the enormousest. 12 plus 1 is 13. 7 plus 5 is, in fact, I should just look at the previous one. 7 plus 5 is 12. 12 and 1 is 13. The greatest of those is 13. So that's the earliest time by which we can start the next event after 13. Let's look at this one. 6 and 5 is 11. 12 and 0 is 12. Which is the greatest of those 12? So let us continue on now, and we'll do the final one. 12 and 6 is 18. 12 and 3 is 15. 13 and 7 is 20. The enormousest, for early times it's the enormousest. The enormousest of those is 20. So that means that the earliest we can finish our project will be after 20. Now, let's start. What we do next, we put in, that's 20 and that's going to be 0. Those are going to be the late times. Now we're going to do our backward pass. 20 take away 7 is 13. 20 take away 6 is 14. Now, just to say, what does that mean? It means We could reach here after 14 days, and we'll still have enough time with 6 days to go to finish H before the project is over, and the project will not be delayed. Let's go backwards here. This is a tricky one. 14 take away 0 is 14. 20 take away 3 is 17. 13 take away 1 is 12. Which of those is the least? Going backwards, we pick the least of those. It is 12. The late times, it's always the least of the ones leading into it. So that will have to be done at 12 in order that 1 and 7 will be done before the end. So whatever is the least of the ones leading into it is the late time, the least of the late time minus the event or the activity. So this has only one leading into it. 13 take away 5 is 8. There's no other leading into it. And then this one, 14 take away 5 is 9. And again, what does that mean? If A is finished by day 9, the project will not be delayed. That's the latest time it could be completed. So the key one here is this one. When there are many leading backwards under a backward path, you do 14 take away 0, 20 take away 3, 13 take away 1, whichever is the least of those results, and it is 13 take away 1, 12, is the late time. So early times enormousest, late going on a forward path, late times the least. Now, next concept. What is the total float? Well, let's just have a look at it. The float means the floating time, that there's between the time an event may start and the time by which it must start. In other words, it's the give and take for an activity. And we shall have a look at the, I'll just use an example. Now, here is a finished time chart, and I'm just going to see how do you work out what the total float is. Now, if we look down at the bottom here, we will show you that if we have an event here, the total float will be Y, take away A, and also take away the time for that activity. That will be the amount of give and take that you have for starting an event. In other words, it's the gap between the earliest time it may start and the earliest time it must start, or the latest time it must start. So let's have a look. Let's look at A. A, if I do 5, take away 0, take away 5, 5, take away 0, take away 5, it has got no, its total float is 0. In other words, it's got no give and take. It must be done at the start and take the 5 days. Any delay, and it'll delay the project. Let's go on to B. B, it's the 10 down below minus the 5 above minus the 5 of the time. 10 down below minus 5 above minus 5, that's 0. In other words, that has to take place straight away after that starts, taking those 5 days and no messing. C, 9 take away 5, take away 3. 9 take away 5, take away 3 is 1. That means that there is 1 day of give for activity C, meaning that supposing that's plastering the walls. Supposing the plasterer rings up and says it can't come today, it'll come tomorrow. You'll say that's fine because we have a total float of 1. We can delay the start of that activity by 1 day and we will not delay the project. So there's a give of 1 day for that activity C, but there's no give for activities A and B. If they ring up and say they're not able to do it, you'll tell them, well, you've lost the job, I'm getting my friend down the road to do it. D, 13 take away 10 take away 3 is 13. Is not 13. It's 13 minus 13 is 0. There's no give or take for event number D. F. 15 below, take away 8 is 7, take away 4. 15 take away 8, take away 4 is 3. So F, the F could be delayed by up to 3 days, and we wouldn't affect the end. A, B, C, D, O. That's 15 take away 8, take away 4. By accident, I had E written down as F. So E is next. 10 take away 8, take away 1. 10 take away 8, take away 1, which is 1. F was 3. G, where's G? Here. 15 take away 13, take away 2 is 0. And lastly, H. 15 take away 10, take away 5. 15 take away 10, take away 5 is 0. Now, those are the total floats, and they are the give that you have to get those events, those activities, started. What are the critical activities? They're the ones with 0 float time. They are A, B, D, G, and H. They are critical activities. Any delay in those activities will delay the project. What are 2 critical paths? Now, critical paths are paths which are made up only, exclusively, of critical events. Now, there is a critical path. Any path that goes from A to H using critical nodes is a critical path. You could go from A to B to D to G. That would be A to B to D to G is a critical path. Each of those, one after the other, will take us to the end, and they add up to 15 hours. So any delay in any of those would delay the project. Another critical path is A followed by B followed by dummy followed by H. A, B, H. You don't put in the dummy, but if you're going from A to B to H, that is a critical path. You'll notice that 5 and 5 and 5 adds up to 15. Those 3 activities take place one after the other, and they take the full 15 days. So any delay there would delay the project. So those are 2 critical paths. Saoirse says the total time for activities in any 2 critical paths must be the same. Is she right? Well, the total time of A, B, D, G is 5 and 5 and 3 and 2, 15. A, B, and H, 5 and 5 and 0 and 5 is 15. Of course it is, because it will be the length of time for the entire project. So, of course, Saoirse is right. Now, if activity F was supposed to start on a Monday, but it has been delayed, what is the latest time this week that F could start the project and be completed on time? Well, this is to understand what does total float mean. F has a give or take of 3 days. So if it was supposed to start on a Monday, if it started 3 days later, Tuesday, Wednesday, Thursday, if it started on a Thursday, it would be the project would not be delayed. You could start it 3 days late. That's what total float means. It means the give or take time for starting F. So if F started by the Thursday, we'd still get the project on time. Those are the basic concepts for activity charts, and that is we're going to continue this with the second one, which looks at actually scheduling and assigning workers on items called Gantt charts, which are used on every building site. I believe all my engineering friends tell me they use them all the time. Thanks very much.